before I start, you will see the topic is rare metals and new technologies. And really that is all that was given to me. My line manager, who's Sagren, was supposed to do the talk, and then Robert Sikuda above him was supposed to do the talk, and so it filtered down to me. It seems like I'm the only one that had time in my diary. I did not get any directive but the title. So the disclaimer I'm going to give you is the front page got CSIR on it. The rest of the slides do not feature CSIR. This is very much information that we've gathered. As I said previously, we looked at advanced materials as well as advanced manufacturing. So it's various sets of information and is very much just what I compiled. I'm not representing the CSIR on this. So please do not take them on any of the things that I'm sharing with you, except the Titanium Center of Competence. There you go. So first of all, I had a bit of difficulty. We all know rare earth elements. I think the one before him mentioned it. I'm not an expert on rare earth, so I thought, what is rare metals? Because that is really what the instruction I got. So first of all, a metal is considered rare, first of all, if you quantify it by its abundance. So if you cannot get it commonly available, then it is called rare. Or the second type of definition is a metal can be rare because it's difficult to manufacture. So titanium is considered also a rare metal. It's not a rare earth, but because of the difficulty in the manufacturing technique. So there's a total of 89 existing elements. I think we all know that. And then gold and silver, which is also rare in abundance, not silver, but gold, is not called a rare metal. They are precious metals. So if you look at all these academic definitions, you can get totally confused. And I think we can almost put in any metal there, because if it's rare to me, then it's a rare metal for me. So I decided to go with, well, I'll show you now, with what is considered rare in terms of abundance and manufacturing. So titanium beneficiation in South Africa. These are just 3 slides on the Titanium Center of Competence at the CSIR. Originally it was not part of the presentation. I quickly put it in this morning, which I'm now glad I did, because I see some people that most probably would hold it against me if I didn't show at least the Titanium Center of Competence, although the majority of the talk is not about it. The Titanium Center of Competence is really a consortium. It consists of science councils, academic institutions, and they are doing research in various fields of beneficiation of titanium. This comes from primary metal production right through all the production technologies and developing of manufacturing methodologies that can be implemented. So I know the pictures on the slides are a bit small, but I'm sure if you just Google it, you will find more information on the Titanium Center of Competence. So there is an activity already. It's been in existence for 11 years. I think last year was 10 years. So we're in 11 years now in South Africa. It's a DST initiative, funded initiative, which is trying to make impact in the sphere of the titanium industries. So I'm not going to look at the longer term visions of what it wants to or the outcomes it wants. It's just know that it does exist already. So the titanium value chain is shown there on the screen. The difficulty is there is no really titanium industry in South Africa, although we have a lot of titanium oxide from which you can make the raw metal. Also, we do not manufacture titanium. We export the titanium dioxide, and we do get in the titanium metal. So there is an opportunity that was missed. So DST thought it wise to invest in research to bring this home. So you will see at the bottom as well all the TRL levels at which certain technologies at the CSIR are already, and also other institutions. So I can say up to now we're much more successful in downstream technology development. Those are your manufacturing processes like welding, rolling, forging of titanium alloys. Primary, a bit more of a challenge, although we are producing powder. Will not please note we are producing powder in small batches. It's a chemical process, and there were more challenges than were anticipated. Not with the chemistry as such, but in the manufacture of the systems that can handle the chemistry. It's very, very aggressive, so it destroys the pots in which you were supposed to manufacture it. And so the chemical engineers were very clever. They could come up with a chemistry that can result in it, and then the engineers missed the point in the challenging chemistry they had to deal with. So there was a bit of a communication gap, but that is sorted somewhat for now. Then we focus very much on the titanium powder industry and developing, because we have the primary metal production and what else you can do with the titanium powders. So all the other normal powder metallurgy processes are being developed, as well as additive manufacturing, where we work with the National Laser Center, as well as the Rarest project for large components. So those were the 3 slides on the titanium and the activities already taking place, well established. Not going to go into too much detail on that. Now I'm jumping back to rare metals. So if this presentation looks haphazard, it is haphazard. And if it makes sense to you, that's also good. That was also my plan. Okay? So the difficulty is in where to pitch it. So there's a lot of information in. So there was this author, David Abraham, that authored the book, The Elements of Power, and he calls metals, rare metals, those elements whose total annual production can fit into just a few rail cars. So if your annual production rate is low, it's a rare metal, and there you go. He also says we don't realize that the products we need today are more tied to the ground than ever, and I think that links to the mines. And the green products themselves are even more tied because of the materials that they rely upon. So everybody is seeing the need for green manufacture, getting the minerals, the metals out of the ores, as well as recycling. So we know wind turbines, solar panels, home batteries, all of these technologies, you've heard it this morning, it's cell phones, toothbrushes, they contain rare metals. So as the demand for green technologies rise, so will the demand for the rare metals that is in them. So there's rare metals and there's the rarest metals. So I decided to focus on the rarest metals. So if you look on the graph, you will see everything in the red is the major industrial metals. That is what we're familiar with. Those are your copper, zinc, nickels, chromes, iron, etc. Precious metals are in purple. And the rare earth elements, which a lot of people think rare metals is only rare earth elements, it's not. They are indicated in blue. And those are the ones with the strange names, neodymium, europium, all those other strange names. What I like is this yellow little band here at the bottom called the rarest metals, because that makes sense to me, and them I understand. So it's ruthenium, rhodium, palladium, tellurium, rhenium, osmium, iridium, platinum, and gold. So even gold is rare. If you look on the y-axis, you will see it's the abundance. So I decided, okay, this explanation of rare metal suits my personality best, and this is what I'm going with. Okay? So you are more than welcome to disagree with me. At least I've got a reason why I've decided on this. So I'm not talking about the rare earths. I'm sure somebody is going to talk about rare earth elements later on in manufacturing and how to leach them. I'm going to look more on the metallic side. So first of all, when I start any studies, I just go and look what is the prices. Because you see the value in something if it is a valuable or very pricey commodity. So, and it was very quick to find from Bloomberg's site. I got this, and it just shows the price performance in 2017 of ruthenium, iridium, rhodium, palladium, and wheat, not a metal, no, and then alumina and lead. And you will see that the ruthenium, iridium, and rhodium stand out among the commodities. So they are rare metals and they are very expensive. So if you want to make investments, obviously you can invest in this if you've got a couple of million, maybe a billion. But then again, also what you need to be careful of, prices are not a measure of the long-term physical or economic availability of a commodity. And because they are rare, they can also be scarce. So it's sort of like a trade-off. You'd never know when the prices will fall because of scarcity. Okay, so it looks like that is a good investment. And then I look at rare metals, but you cannot see them as a singularity. You must see it as part of a material, because they're all part of materials. I'm thinking with an engineering brain, you never just walk around with okay, maybe gold, because it's rings and jewelry, but never just a piece of cesium in your hand. It's always part of your cell phone, etc. So why in general is the bigger group of materials important? First of all, for the economy. So materials are the pillar upon which most manufacturing is built and create more high-skilled jobs per income earned. This is global. So if you want to stimulate high-income earners in a country, you need to stimulate the materials manufacturing sector. That includes metals and all other materials. Then also societal needs, address need for better environmental stewardship, increasing water and energy usage, and decreasing health and nutritional needs. So all of this falls under materials. Actually in MSM we also have people working on biomaterials. And on this side we do welding, and on that side they do nanoparticles. Such a wide range of where materials can be picked. The little sketch I showed you there is just one sort of industry, and that is lighting. If you look at lights, and we can start off on material scale $10 billion, but the effect later on is a $700 billion market. So sometimes you do very cheap, well, relative cheap research, but the impact in an industry where it's going to be used is so much bigger. So now I'm doing a plug for the researchers, when we come to you with an idea, please be kind to researchers, because the bigger economy can benefit greatly. So what is the complexity of modern materials? Unlike normal materials, which you can classify according to chemical bonding, all the advanced materials or systems are often classified according to function or scientific classification. So some of you can disagree, you can agree, you feel free. First of all, you get multifunctional materials. Very rarely these days that you get a material that is purely only for one specific purpose, except maybe electrical conductivity. Then you get multi-structural materials, lots of different structures. Metamaterials and artificially structured functional materials. Oh, I sound very clever with all these words. Nano-enabled materials, bio and bio-based materials, materials with target surface properties, conductive, non-conductive, etc. Metals, this includes your metallic glasses or your amorphous metals. You have ceramics. It's not a metal, but you get magnetic ceramics, you get technical ceramics. That also is a very big market. And then you get your polymers and soft materials. And soft materials can be anything from gels to soaps. So it's a complex world, and they all interact with each other. Try to always tell the design engineers, very much I used to be a lecturer for many years. The first year students, if you give them a design little project and say, make something for you, they always choose steel because that's all they know. That's all they know. So there is so many materials these days available that it is important to know from the beginning what you're going to use. So what are the global markets for advanced materials? Key markets by 2030. Number one, the energy market, 37 billion euro market. Okay? So there will also be, if you have fancy metals in. Environment, and these will things like water purification systems, etc. 86.8 billion euro. Healthcare, 55 billion euro. Healthcare includes things like implants. ICT, communications, 70.7 billion euros. Transport, which is aerospace and automotive, 24.3 billion. So these are global big markets. And if you think how rich South Africa is in resources, actually the whole of Africa, the global economy cannot really be without the resources that we have as a country and a continent. It makes us very powerful, but big responsibility on government as well to make sure that it is managed sufficiently. So globally, the advanced materials will contribute $57 billion per annum to a broader material sector by 2022, and they predict a 13% annum growth versus a 3% for conventional materials. So all these fancy metals, alloys and materials will have a bigger growth rate than normal steel, aluminium, magnesiums, So the South African overview, by no means, I'm not the expert here. Got this from Stats SA. They've got these spreadsheets full of metal data. So raw materials in 2017 contribute 48.1 billion rand, while value-added materials contributed to maybe 143 billion rand to the country's GDP. This is 2017. So what this tells you, let's first continue. The industry employs approximately 500, more than 500 if you take the secondary processes as well. And then significantly beneficiate local resources. Then there's sort of a graph there, and the blue line on the top, the big line with the big spike, that's your iron ore. Okay, that's still the biggest ore export that we have. So that is the ore and concentrate balance of payments. Then the other one is the value-added materials balance of payments. And the last one is the assembled goods and equipment balance of payments. And that one is more worrying. You can see the downward trend there and even into the negative. So that is where we are assembling and exporting. So to make an informed decision, you need to know these things. And you will see these trends come from 2008 right through. So it's quite a couple of years. It's not just a quick study. So what does the graphs tell you? Ore and concentrates is still the biggest influence in the market. Value-added materials are low to stagnant. There's not really any growth there. And assembled goods and equipment also stagnant or even to the negative. So maybe why we looked at this is because I like industry, I like the manufacturing industry. So how do I go out to an industry and say, invest in R&D and I can help you manufacturing if he's not even sure that he's going to have business in a couple of years with all these negative trends. So you need to know, unfortunately, all of this information. So luckily, South Africa, we're not looking bad in terms of these minerals and these fancy metals. If you look at the palladium world production, we're second biggest, South Africa. I think this is 2016 or 2017 data, I might be mistaken. Only Russia exceeding us in production. Gold world production, you'll see there's plenty of players in the gold world production, but South Africa at least also featuring there with a 7%. The platinum world production, we are leading, 75%, which I think we've cornered the market in platinum production. And then the platinum group metals world reserves, 95%. Somebody showed, I think, 87%, but we can more or less say 90% of the platinum group metals world reserves is in South Africa. Once again, gives us a lot of power in terms of that information. So, rare metals. The problem is they are mainly mined as part of a byproduct of other minerals. Okay? Selenium and tellurium are extracted from copper slag. As a byproduct, they are cheap to produce. But if you have to mine it on their own, they would be very, very expensive. Thus, even as the demand for rare metals increases, the supply could remain static because the supply is based on the other metal, which is mainly mined, like in this case, copper. So if the market for copper doesn't grow, then it doesn't matter if your rare metal market grows, you cannot get more of it. So obviously that will increase the price, and we might have to go and get an asteroid or two maybe, I don't know. Maybe then it would make sense. So the production steps I've just listed there for interest, showing that there's quite a lot of technology areas. So from extraction right through to the manufacture of components from the alloys and the alloy design. And each one of those little points there is a science or an engineering discipline in its own. And we work very sort of, I wouldn't say segregated, but I mean, I'm in the manufacture of components. That is where I feel comfortable in. Then there's people from mining and extractive. They work there in the extraction of the, and sometimes in between some of the steps, people get missing and the communication, there's a communication gap. So how do I educate the next set of engineers to be sensitive in design, knowing that they have to take into consideration the mines, the recycling, etc., if the people doing mining engineering do not tell me their needs? So sometimes there needs to be a bigger forum where these people just share information. So maybe this is not a bad forum for that type of interactions. So the common technologies these days, and I'm just listing them because these are not new or emerging, they already exist. So these are your storage batteries, fuel cells, nuclear power, vehicle lightweighting, catalytic converters, photovoltaic cells, and thermoelectrics. And then the key elements in them, some of them are rare, other are not so rare, and they range from lithium right through. At the bottom you'll see various REEs, and REE is rare earth elements. So this is common technologies that is currently being used. So we're comfortable with where these metals are being used